Okay, hello everybody, this is Dr. Hassan again in Power Electronics. This is module number 2, controlled AC to DC and DC to DC converter. This is the week number 4, where we are going to discuss AC to DC controlled converter first, and we introduce the DC to DC converter. Now let me start with single phase control rectifier, and then I go to 3-phase control rectifier, but control one now. Here when we say the control, it means we are going to use either thyristor, transistor, switch, something we can control, not diode. Okay, so the same discussion for single phase and the 3-phase. For diode, we'll repeat it here, but for thyristor. Also, we discuss half wave and full wave. We will repeat the discussion. Also, we discussed at that time ideal supply and non-ideal supply when inductance is considered and commutation and overlap occurred. So the same thing will be done here. As you can see here, either we have supply single phase, 3-phase, we have rectifier here, use thyristor. Okay, and it's worth mentioning, since it's control device, thyristor or transistor, then the power could go from the supply to the load or from the load to the supply. As example, if we have on the load motor, it receive energy. If the motor, DC motor, if the DC motor work as a DC generator, it's returning back the energy. For that, we are working in these two, let me say, quarter. When a VD, ID, both of them positive, we are rectifying the signal, the AC signal. When VD is negative, as you can see here, minus VD, then we are inversing, I mean returning back of the energy from the load to the supply. Now, for half wave rectifier, similar to the previous discussion for diode, but the difference here, yes, here there is positive voltage applied, but thyristor will not work until it get pulse. Okay, pulse signal going to the gate. So in this situation, we have here. So what we have here, we have here the signal appear in this way, 0 until alpha coming, and then the voltage appear across the load, and the same thing, the current will appear, and then it go to 0 at this point pi, where the thyristor cut off and shut down. Now when we have inductive resistance load, similar to the behavior happened in diode circuit, but the only difference here, we don't start at 0, we start at alpha. As you can see here, whenever there is pulse, we started current increase gradually, and the voltage appear across the load. Yes, the voltage here at pi, it will be in reverse bias, reverse direction, the thyristor should be off, but what happens is the inductance enforce the thyristor to keep conducting until it releases its energy. So we see that negative part will appear across also the load. And the same circuit have been discussed in diode situation, the same behavior. You remember at that time we mentioned that here at this point of intersection, the voltage V will increase beyond the back EMF at the supply here, at the load, sorry, here. So the load will receive current. Okay, current will be conducted. But what happens is, for thyristor we cannot until, you see here, until alpha came. Hey, this is alpha came here. Yes, there is forward voltage, but it will not appear, still the back EMF appear across the load. But at this point, when alpha came, thyristor will conduct, and we will see the current and voltage appear across the load. The same discussion, the same explanation. The only difference in equations here, we will not start from 0. We always start from alpha, as you can see here, 32. Okay, which is alpha. Always we start triggering angle. Now, or firing angle. They call it trigger angle or firing angle. How triggering of thyristor happen? How we generate pulse to the gate? Now we take from the same supply, and we use a transformer to step it down. What we want from this is to get the same signal in this way. Okay, we want to know these points crossing zeros. Okay, we want to record it because we are going to measure alpha with respect to them. Now here, this signal, small signal, having the same input signal behavior and waveform. Now sawtooth came, this is sawtooth. Okay, it will sawtooth generated based on this crossing point. Okay, zeros. So this 0 start and end at the second 0 and at the third 0, and so on. Now we will compare the sawtooth. We will compare the sawtooth with the with the linear control signal, which is DC voltage. I will show you how to produce the pulse. Now this is the input signal. As you can see here and here, we produce the sawtooth at this crossing point, and this is the control signal. Now we make a controller to say that whenever the sawtooth signal higher than the control signal, give pulse. You see here at this point the sawtooth is higher than the control, so we have pulse. And the same thing here and here, it repeats itself again. It's represented by this formula, which say that V control based on sawtooth maximum voltage will give the firing let me say angle. Now the same discussion, full bridge single phase and full bridge three phase. Ideal, let me start with ideal. This is similar to single phase diode circuit rectifier. Now if we make the pulse at zero time, then it will behave like a diode. The whole waveform will appear. But if we give it at alpha, then the situation is we start conducting at alpha. Sorry, T1 and T2 will conduct for part of the time, T3 and 4 will conduct for the next part of the time. As you can see here, this is the signal at this point here. The thyristor voltage is forward, but it will not conduct until alpha came, as you can see. Then the voltage change from D3 and 4 into D1 and D2, and it continue until the next diodes D3 and 4 will conduct. 3 and 4 will be conducting, and then it will so it will conduct the current. So if we compare the signal for diode circuit, it will be like this, but for thyristor circuit it will be like this. Okay, so we see that part of it going in the negative direction from alpha into pi over alpha plus alpha, okay, to the next the end of the cycle. The same signal here, this is V maximum sine omega t. Sine will be integrated to be minus cosine, and then we will substitute. We got this formula. Now this formula tell me that, let me split them. Okay, in full bridge diode rectifier circuit, we mentioned that it's 0.9 Vs. Here it's multiplied by cosine alpha. So cosine alpha, when alpha 0, it's behaved like a diode, so cosine 0 will be 1. So we back to the diode circuit. When alpha increase, the output voltage will be reduced, because we go to the negative part of this. Negative part will cancel part equivalent in positive. Now this is the ideal in diode situation, as I mentioned, and we have a drop. The drop is the ideal, so 1 minus cosine phi represent the dropped part. If I multiply current by voltage, it will give me the power, real power. Okay. Now it's worth mentioning that if I sketch the normalized value of output voltage, the real one with the ideal one, okay, with respect to alpha, I will see when alpha lower than 90, the thyristor behave as in rectifier mode. It means the power coming from the supply to the load. When it is behind, let me say 90, above 90, it's work in inversion mode from the load to the supply. The energy back from the load to the supply voltage will be in negative. Okay, the same graph for the line current, input line current is a square wave. We assume here that highly inductive load, but the only difference here is there is phase shift between voltage and current. This phase represents alpha, firing angle. Also the spectrum, we can see that there is third, there is ninth, and there triple harmonics is there. Now in this circuit, as you know, we have P power, real power, active power, reactive power. So if I come to represent the instantaneous current, supply instantaneous current, we will have the fundamental, the third, the fifth, and so on. So if we use this formula to find IS1, then IS1 will be 0.9 IS, and we define supply current harmonics to be the fundamental, fundamental pair, the harmonics, and IS similar to the diode will be equal to ID. Power, total harmonic distortion, also calculated in the previous part, and cosine power factor, cosine alpha will be the displacement power factor times 0.9, which is the ratio IS1 over S, which give me the power factor. Now from level 2, you know that power P is VSI as cosine phi, and we can substitute for the voltage by its value, which is 0.9 cosine alpha. Then we have this formula. Now the same thing for reactive power Q1 is VSI as cosine phi, and we can find the apparent power by taking the square root for P square plus Q square. It's almost the same discussion for that, but the only difference is we started from alpha, not from 0. When we have inductance here, commutation will occur. But have a look, we already have delayed, which is equivalent to alpha. What is else? We have commutation. Commutation, if we assume it is linear, commutation this way, linear, not with a curve, then this part from here to here is u. So half of it will we reach the 0 point, so it will be, the phase shift will be alpha plus half u. Okay, so this is here. The other waveform is more clear. From here to here, we can see there is alpha. We wait for the firing element to come, and then here commutation occurred for a while, which is u, where short circuit occurred, and the current and voltage will be 0. Voltage reduced. We need to consider this similar to the formula, driven formula in the previous discussion for the diode. We repeat it here again, but rather than from 0 to u, it will be from alpha to alpha plus u, as you can see here. We did the integration for sine minus cosine, and here it will give id, and we go through this simplification until we get this formula. What the formula tell me? The formula tell me that cosine alpha plus u, in the diode there is no alpha, it's directly